Lagrange multiplier. Let's go through this theorem here. It speaks about the definition of what the Lagrange multiplier is. So the theorem says, let f and g be functions of two variables with continuous partial derivatives at every point of some open set containing the smooth curve gxy equals 0. Suppose that f, when restricted to points on the curve gxy equals 0, has a local extremum at the point x naught, y naught, and that the gradient of g is not equal to 0. Then there is a number lambda called the Lagrange multiplier for which the gradient of f equals the lambda gradient g. So what that's saying here is that the gradient of f and the gradient of g are going to be parallel vectors. That's what that's saying. So this lambda here could be positive, could be negative. So it could go in the other direction, but nonetheless, they're still parallel vectors. And hopefully we understand that gradients are, they call them gradient vectors, which means they're vectors. So just keep that in mind. So the Lagrange multiplier is this lambda that we times by the gradient of g to equal the gradient of f. So this is all the idea here for this next type of problem. And it doesn't matter what we do with these. That's what it is. Now, the main purpose of this Lagrange multiplier and this process here is essentially what we're going to do is, given any surface, if we restrict that surface, say we cut it off at this path here, then what we're going to find on this is we're going to find where the maxes and mins are on this path. And that's essentially what this process is doing. It actually is set up in such a way that we will find those maxes and mins. So let's say this is happening with our surface. Let's say it's doing this, because it could drop down because of contours and stuff in the surface itself. And we could see that this here would be a maximum and over here would be a maximum. And we could probably see here that this would be a minimum. Now again, we're only finding maxes and mins on the boundary. That's what we are doing when we're using this process with the Lagrange multipliers. So I just want to keep that clear to you. So now, if we think about it that way, let's say we have a surface that's a little bit more erratic. Okay, and let's say we are looking at this here. And let's say this, when we try to draw a curve to cut it off, our path. So what's going to happen here is we're going to have a minimum here. We probably have one here, probably have one there. And again, these are just for the past. That's what the Lagrange multipliers would find. It would find all of those. That's what this process here does. That's a process, and you just don't know it yet. But we'll see it as we move along. But that's not the highest point here or here. So that would mean that we would have to consider the interior as well. So that's essentially where we're going to get to. We're going to talk about bounded surfaces, and with those bounded surfaces, we're going to talk about maxes and mins, and not just the maxes and mins themselves. Are they saddle points also? And also, are they the absolute max and the absolute min? And that's where we're heading to with these Lagrange multipliers. So we're going to actually make our surfaces bounded, and that's what this g of x truly is for us here. And we'll see what that is below. So what we're going to do first here is we're going to find the gradient of f and the gradient of g. But I want to clarify g a little bit more. G of xy is really equal to 2x squared plus y squared minus 1 equals 0. Even though this is the equation here, look at what I have for my g of xy. It has to equal 0 there. So what I'm going to have to do is move the 1 over so that I will be able to accomplish that. So it's really just this here. That's what my g of xy is. So now what I'm going to do here is, I know my f of x is this function here. So now what we're going to do is we're just going to find the gradients of each. So the gradient of f, And the partial of this with respect to x is the first thing. That's going to be my fx here. That's going to be 12x squared. And then for my y here, for the same function, it's going to be 2y. So there's my gradient of f. Now let's go to the gradient of g here. So the gradient of g is going to be for x. And with respect to x, yep, and the gradient of g for the y component, it's going to be fy, which is 2y. And just remember here, those all go to 0 because the derivative of constant is 0. So there's my gradient of g. So now we have the equation. And we're just going to follow this one right here exactly. So that means the gradient of f, which equals 12x squared, comma, 2y, is going to equal lambda g, so lambda, times 4x 2y, and that's equal to my lambda gradient g. And that's what we see here. Gradient of f equals lambda gradient g. That's what this is here. Okay, so now that gives us equations here. Because if vectors are to be equal, their components have to equal each other. So what that means for us is we end up with the equation 12x squared equals 4x lambda, and that's one of them. And the other equation becomes 2y equals, and that's going to be 2y lambda. So initially I'll take the 2y and subtract the other one over and get equals 0. Then I'm thinking factoring. Most of the time we're dealing with any of these, the idea of factoring has a tendency to come up most of the time. So 2y, that's going to be 1 minus lambda equals 0. And again, from these two equations, we're just trying to get whatever possible information we can get from it. And a lot of times when we do this kind of process, we could end up at a dead end. So just be aware of that too, that there's no set way to do this. A lot of it's just trial and error, just trying to go through the process and see if you can get something that seems feasible. So this means from this equaling 0 here, that means y equals 0 or lambda equals 1. So that's what we're going to use now. So we just take the cases there. So where y equals 0, then what I can say for the other equation is, not the other equation, so keep in mind here, it's not just solving a system of equations anymore. We are trying to get information on the boundary. Now this g of x here is actually the boundary that we're intersecting with our surface. And this, I don't know if you caught this, but this is an ellipse. And it's projected up to the surface. So it might not look like ellipse when it hits the surface because we got angles and stuff up there, so we can get a lot of weird looking shapes where this actually intersects with that surface. Because it's just like a cylinder, elliptic cylinder. So if y is 0, then I get 2x squared equals 1. And that's kind of what I had before. I can move the 1 over, or divide the 2 over. So then I'm going to get x equals plus or minus 1 over square root of 2 once it's simplified. So this gives me 2 points here. So the first point is going to be 1 over square root of 2, comma 0. And the other one is going to be 1 over square root of 2. Make sure that's a negative there, though. Because remember, we got the plus or minus here. And that's comma 0. So that's our second point, dealing with just the case of y equals 0. We also have lambda equaling 1. So keep in mind here, this lambda we're going to have to plug into the other equation simply because we have no lambdas up here. So if we get that lambda in terms of x's and y's, then we can sub it in our boundary there and then maybe get some more information about this graph here, bounded by that gxy. Okay, so anyways, so now what we're going to do is we're just going to plug that in there. So that's going to be 12x squared minus 4x, and then lambda's 1, so equals 0. So this is really 12x squared minus 4x equals 0, and I could pull a 4x out, and that's going to be a 3x minus 1 equals 0. So that tells me x equals 0 or x equals 1/3. So those are my two answers from that one, which give me another 2 points once I plug them in to the boundary. So now I have to plug those into here. See what I can reason from that. So I moved everything over to the other page. So here it is. And let's just finish this problem. We left off here with those two answers. So now we got to plug them into our constraint or the boundary and figure out what those y values are for those. So then we have ordered pairs. So if x is 0, that's going to be 2 times 0 plus y squared equals 1. And that's going to result in 0 there. So really y squared equals 1, so y equals plus or minus 1. Once I square root both sides, finish the process. So my ordered pairs for that. Now remember here, we're still on lambda equals 1. I should say continued. Okay, so there it is. So it's coming from up there still. Oops. Okay, so then my ordered pair for this are going to be, my x was 0. Actually, yeah, I had two conditions here. There's one of them. I'll leave that there. And I also had x equals 0. All right, cool. All right, so then that's going to be the ordered pair 0, -1, and 0, 1. Okay, now the next one here, we're going to need our, still it's lambda equals a 1, but my x is going to equal 1/3. And that's going to result in wrong equation. There it was. Sorry about that. We gotta plug it in the boundary, which honestly is just this one down here. Glad I caught that. That would have been annoying. So that's gonna be 2 times 1/3 squared plus y squared equals 1. So that's gonna be 1/9. So honestly, we just have 2/9 here plus y squared equals 1. So when I move that over to the other side, I subtract it. So I'm going to get y squared equals 7/9, and then square root both sides. So y equals plus or minus square root of 7/3. And that's going to be the other values for that. So then those values are x is 1/3, and my y is negative square root of 7/3 for the first point, and then 1/3 for the second one. That's a positive square root of 7/3. So there's the other set of points. So those are all of our points for this. This is going to take up a ton of space just getting to these answers, because I'm trying to reason every possible example with these to try to gain information that I can plug into the boundary and get the y values once I find x values, or vice versa. If I find y values, then I can plug those in and get the x values. So now I have 2 points here, 2 points here, and I'll go back to that first page, and I had 2 points here. So altogether, it looks like we have 6 points to actually consider here. Seems like quite a bit, but honestly, when you're dealing with these problems, it's not. It's probably average. Believe it or not, we are almost done. So now what I'm going to do is I'm just going to make a list of all of the points and just put them here. So I have 0, -1, have 0, 1, and now I'm going to continue to just put the list in. Now remember, all of these points are either going to be maxes or mins for the points on this boundary. Now remember, we're on this ellipse here when it's projected up to the surface, and we found 6 points that seem like highs or lows. So now what we're going to do with those is we're going to classify them and find out, are any of these maxes, or which ones are maxes and which ones are mins. And that's what we're going to do now. And all we have to do is just plug in the function value. And the largest value wins for maximums, and the smallest value wins for minimums. And that just goes back to what it said. It said, use Lagrange multipliers to find the maximum and minimum values of the function, subject to the constraint. So now we're just going to take f of 0, -1, and just plug that in. So it's going to be 4, 0 cubed plus -1 squared, and that's going to result in a 1. So then f of 0, +1, it's going to be 4, 0, cubed plus 1 squared, and that's 1. So then I'm just going to keep going through the process of these. So there they are. I didn't want to waste the video just doing simple computation here. I did the squareds for the square roots just so you can see what those would look like, and that's the 7/9 that you see over here. Squaring the square root of 7 is going to be just 7, and that's what happens here. But if you look at all of these answers here, 7/9 is, oh, excuse me, wrong one. 25/27 is smaller than 1, because 27/27 is 1. Square root of 2 is 1.41. So the way this looks here is this right here will be a max. Okay, and that's the 1/√2, 0. Okay, and then now I'm looking for the smallest number here. And the smallest number here is going to be this negative square root of 2, which is this one here. And all the other ones fall between. So this would be my max, and this would be my min. So now I want to show you one more thing before I end this video. So just kind of remember the negative square root of 2, -1 square root of 2 is going to be my minimum, and the positive is going to be my maximum. And that's on my x values. Notice that. Because where the y's are 0, that's right on my axis. So I want to show you the pictures of these. Oops. Here they are. This is what we're looking at. And remember, we had 6 values. So notice this. There's going to be 1 here, probably. There's 2. Maybe. Yeah, that's right. There's 3, and I'll circle that one, because that one's the one that's there. And then I have this same look on the other side, where I will actually find the other 3. So it makes sense why I have 6 all together here. As you can see the picture, you can see how they dip. And what I mean by that is I'm looking at how it intersects. So you can see that looks like it goes up, and that looks like it goes down, that looks like it goes up again. So those are going to create those maxes and min scenarios. And we can see that a maximum is going to be here. Now here's my x-axis, and where the x shows, that's the positive side. And that would have been that 1/square root of 2 there for the x value, how far I'd come out. And if you look at the other side, that's also on the x-axis. There's the x-axis right there. And that's where that minimum's happening. And then I also did a side view here. I thought this was kind of nice. So you can kind of see how this comes up and dips in also. So if I was going further, let's say I was also doing the interior, which if I use an inequality here instead of an equal sign for my constraints. So if my g of xy was equal to 0, or if my g of xy kind of had a less than or equal symbol to it, then that would change things. Not less than 0, but whatever it is. So there's our answer for this, and I just kind of want to give you a visual of what it looks like.